Hey everyone, welcome back to the deep dive. We're here to, dive deep into some of the latest and greatest research papers and, especially the ones that make your head spin a little.
Exactly, those really dense ones that sometimes leave you wondering, did I actually understand anything? But that's why you're here, right? To cut through the jargon and get to the heart of the matter.
Absolutely. And today we're tackling a pretty hot topic, something that just landed on ArcSieve last month, March 2025, block diffusion language models. Block diffusion language models. Have you had a chance to glance at this one yet?
I have, and it's pretty fascinating stuff. It's all about blending two big ideas in language modeling, like, taking the best of both worlds.
Right, the tried and true, the autoregressive models, and the newer kids on the block, diffusion models, and somehow they're making them work together.
Yeah, it's like they're taking those classic AR models, like your GPTs and all, and finding ways to overcome their limitations.
By borrowing some tricks from diffusion models, it seems.
Yeah, and I think what's really cool here is that we're going to get into the nitty-gritty, like not just what they did, but why they did it.
The algorithms, the math behind it all. It's going to get a little technical, but hey, that's what we're here for.
For sure, we're going deep. And speaking of going deep, our main source, of course, is the paper itself. Block diffusion, interpolating between autoregressive and diffusion language models. Catchy title, right?
Rolls right off the tongue. But don't worry, we've also got our trusty all notes doc, which gives us all the backstory.
Yeah, it's like a peek behind the curtain, gives me a sense of how the research evolved, who the key players were, that kind of thing.
Love those behind the scenes insights. Okay, so first, let's set the stage here. Before we get into block diffusion itself, we need to talk about the two approaches it's trying to marry.
Right, the fundamentals. So on one side, you have your autoregressive models, the AR models, and like I think everyone knows by now, this is like the bread and butter of language generation.
Your GPT-3s, your whatever the latest GPT is by now.
Exactly. And the basic idea, right, is that you generate text token by token, one after the other. So like to predict the next word, you look at all the words that came before it.
Makes sense. And that's represented in like equation one in a lot of the standard textbooks on this stuff. Not in this paper, though, because they figure everyone knows that part by now.
Yeah, it's kind of assumed knowledge at this point. But the key thing is this sequential token by token approach, it makes training really efficient.
Right, because you're just predicting one little piece at a time. But there's a downside, isn't there? I mean, there's always a trade-off.
Oh, yeah, for sure. And the big one with AR models is that the generation process itself can be really slow, especially when you're dealing with like long pieces of text.
Because you have to go through the entire network for each new token, recompute everything.
Exactly. Each step requires a full forward pass. It's not like you can reuse calculations or cache stuff like you can with, say, some block-based approaches. There's no built-in mechanism for like key value caching across the entire generated sequence. You can really bog things down, especially when you're trying to generate something on the fly.
So that's your classic AR model. Great for training, not so great for speed, especially during inference. And on the flip side, we have these discrete denoising diffusion probabilistic models, D3PMs. So how do those work?
Okay, so D3PMs, they work in a kind of different way. Imagine you have a clean text.
Got it.
So you have this clean text and you start adding noise to it step by step.
Noise, like scrambling the words up or something?
Kind of, you're gradually corrupting the original text, transforming it into what they call a latent variable.
Right, represented by next dollar. I saw that in the paper. Changes over these discrete steps.
Exactly. So that's your forward process, adding noise. And then you have the reverse process where you train a model to denoise it.
To get back to the original clean text.
Precisely. The model learns to predict the previous less noisy state given the current noisy one. Step by step, it undoes the noise until you get back to the original text.
Noise in, clean text out. Got it. Now, I know the paper talks about some limitations of these D3PMs, especially when you apply them to language. What are those?
Right. So there are a few key challenges that have, kind of held back these discrete diffusion models.
Kept them from being as widely used as AR models.
Yeah, exactly. So one big issue is that a lot of the current discrete diffusion models are designed for fixed length generation.
So you can only generate text of a certain length. That sounds pretty limiting.
It is, especially if you're thinking about things like open-ended text generation or chatbots, where you need variable length outputs. Then there's the issue of efficiency. Because of how they typically use bidirectional context during the denoising process, they can't really take advantage of KV caching.
Right, which is a big deal for making AR models faster during inference.
Exactly. And then finally, in terms of like standard language modeling metrics like likelihood or perplexity, discrete diffusion models haven't really been able to match the performance of AR models.
So they haven't quite caught up.
Not yet. So you have these two main approaches, each with strengths and weaknesses, and that's where block diffusion comes in, is trying to find that sweet spot to combine the best of both worlds.
Okay, so AR models, efficient training, but slow generation and no KV caching. Diffusion models, interesting approach, but stuck with fixed length generation, no easy KV caching, and not quite matching AR performance. That brings us to block diffusion. So how do BD3 LMs pull this off? How do they combine these two seemingly disparate approaches?
So the key innovation here is that they're taking this hybrid approach.
Hybrid, like a fusion of sorts.
Yeah, exactly. So instead of generating text token by token or working with the whole sequence at once, they divide the input sequence into these blocks. Think of them as chunks.
Okay, so you got these blocks of text, then what?
Then they use a discrete diffusion model to figure out the probability of each block. But here's the key. They do it conditioned on all the blocks that came before.
So each block depends on the ones before it. That sounds a little like the autoregressive approach.
Yeah, it's like they're bringing in that sequential element from AR models, but at the block level instead of the token level. And this conditioning, it's really important. It's actually how they're formally define things in the paper, like in equations 4 and 5.
I remember seeing those, lots of math.
Yeah, they're basically saying that the probability of the whole sequence is the product of the conditional probabilities of each block given its history, and each of those conditional probabilities, that's where the diffusion process comes in.
So you've got this block by block generation, but within each block, it's all diffusion powered. And the blocks are linked together in this autoregressive way. Okay, I think I'm starting to get the picture. What are the advantages of this approach? What problems does it solve?
Well, for starters, it allows for flexible length generation.
Right, because you're not limited by the fixed length of the diffusion model anymore. You just keep generating blocks until you're done.
Exactly. And because you have this autoregressive dependency between blocks, you can now use KV caching.
Oh, right, because once a block is generated, you treat it as clean and cache its states for the next block.
Exactly, which means big speed ups during infants. And then there's another really interesting aspect, which is that within each, because you're using diffusion, there's the potential for parallel token sampling during the denoising steps.
So you can actually speed up the generation process within each block as well. That's pretty cool.
It is, and the paper actually includes figure 1, which I know you can't see, but it basically illustrates these concepts visually. You'd see the sequential nature of AR models, the fixed length of typical diffusion models, and then block diffusion with its variable length block by block structure and the potential for KV caching.
It's like a visual representation of this best of both worlds idea. So we've got the big picture now. Let's zoom in a bit. What does this block diffusion engine actually look like? How do they build this model?
Okay, so the architecture itself is actually pretty elegant. They use a single transformer network as the base denoiser, and the same network is used for all the blocks.
So one network to rule them all.
Exactly. But the magic, the real secret sauce, is in how they design the attention mechanism within this transformer. They use what they call a block causal attention mask.
Attention math. Well, what does that do?
So basically, when the model is processing a token in a particular block, this mask makes sure it can only see other tokens within the same block and all the tokens in the blocks that came before. It prevents it from looking ahead at tokens that haven't been generated yet.
So it forces that block by block autoregressive order.
Exactly. Pretty clever, right?
Definitely. So we've got the architecture now. How do they train this thing? The paper talks about algorithm 1, this two-pass approach, and then a more optimized vectorized method. What's going on there?
Yeah, so training these block diffusion models efficiently, it's a bit tricky. You've got the block structure and the diffusion process within each block, and it all has to work together.
Right. Lots of moving parts.
Exactly. So algorithm 1, the two-pass approach, it's kind of like a stepping stone. In the first pass, you process the entire clean input sequence to pre-compute the key and value caches for all the blocks.
So that's your K1 for all the blocks.
Right, and then in the second pass, you actually do the denoising. For each block, you take the noisy version, feed it into the denoiser, and condition it on the KV caches from all the previous clean blocks.
So the model learns to denoise based on the clean context from the previous blocks.
Exactly, but you see how you're essentially doing 2 full passes through the data.
Yeah, it seems like you're repeating some work there.
Right, and that's where the vectorized training method comes in. It's all about doing this more efficiently. Instead of 2 passes, they concatenate the clean data with the noisy data into one big input.
So you have the clean sequence, tox dollars, and then all the noisy blocks all together.
Exactly. And then they design this special attention mask called MTF that works on this combined input. And this allows them to compute the loss for the entire sequence in a single forward pass.
Wow, so 1 pass instead of 2. That's a pretty significant speed up. What's so special about this $M mask?
It's a pretty ingenious design, actually. It has 3 main parts. First, you have the block diagonal mask, which allows the model to process the information within each noisy block independently. Then you have the offset block causal mask, $M, which allows the noisy tokens to attend to the clean tokens in the previous blocks. That's how you get the conditioning.
Right, so each noisy block can see the clean context that came before.
Exactly. And finally, you have the block causal mask, M die order, which governs the attention for the clean tokens themselves. It ensures they attend to the correct context within their own block and the preceding blocks.
Okay, so this mask is really orchestrating the whole information flow. The paper mentions figure 3, which I'm guessing shows this visually. You'd see how this mask creates this specific pattern of sparsity, allowing for efficient computation.
Yep, that's it. So we've got the training down. But how do you actually generate text with this model? How does the sampling work?
Yeah, algorithm 2 talks about this.
Right, so the sampling algorithm follows that block by block structure. For each block, you have a sampling function, which they call sample, and it generates the tokens for that block.
Based on the KV caches from the previous blocks.
Exactly. Once you've generated a block, you consider it clean, compute its KV caches, and then use those caches to generate the next block. And you keep going until you've generated your whole sequence.
So it's autoregressive at the block level, and as we discussed, this is how they get around the fixed length limitation of other diffusion models. You can generate text of the length you want. They even hint at the possibility of doing some parallel processing within the sample function itself.
Yeah, that's another potential advantage because you're using diffusion within each block. You could potentially parallelize some of the denoising computations. Now, the paper also dives into a pretty important issue that has plagued diffusion models, the likelihood.
Right, the fact that diffusion models haven't been able to match the likelihood scores of AR models, why is that?
So a big part of the problem, and the paper really gets into the weeds on this, is the high variance you get during training. And so to really study this, they focus on a specific type of block diffusion model, the masked BB3LM.
Like they're masking out some of the tokens during training?
Exactly. They randomly replace some tokens with this special mask token denoted as M dollars.
Okay. Kind of like what they do in BERT for pre-training.
Yeah, it's a similar idea, and they have this simplified objective function for this masked approach, equation 8. Now, here's where it gets really interesting. They did this case study where they looked at single token generation. So the block size, $, is just 1.
So you're just predicting one token at a time.
Right. And in this case, the block diffusion objective function actually becomes mathematically equivalent to the standard negative log likelihood objective that you use in AR training. They even show the derivation in the supplementary material, B.4.
So theoretically, they should be the same. But are they?
That's the thing. They're not. When they actually trained the models, they still saw this gap in perplexity.
So in practice, something's not quite adding up.
Exactly. And they figured out that the main culprit is this high variance during training. So when you're training a diffusion model with masking, the model is constantly dealing with partially masked tokens, especially in that single token case. You're essentially throwing away a lot of information.
Because half the tokens are masked out on average.
Right. So the model is getting these weaker, less informative signals, which leads to more noisy gradients, more variance during training. Figure 2 actually shows this visually. You can see that the training loss is much more jumpy for the standard diffusion objective compared to the AR objective.
So it's all about the quality of the signals the model's getting during training.
Precisely. And to fix this, they came up with a pretty clever solution. They redesigned the forward noise process specifically for that single token generation case. Instead of randomly masking tokens, they just masked the entire token all the time. So Q dollars equals MXL equals $1.
So you're basically guaranteeing that the model always sees a fully masked token in that single token scenario.
Exactly. And what's really cool is that when you do this, the diffusion objective becomes completely identical to the AR objective. They show the math in B.4 of the supplementary material. And when they trained the model this way, they got pretty much the same perplexity as the AR model.
So problem solved.
It seems so, and not only did the perplexity match, but the variance during training went way down. You can see this in figure 2, and they even measured it formally using the variance of the block diffusion loss, bar full masking, significantly reduced the variance.
So this noise schedule, the way you introduce the noise, it's not just some theoretical detail, it has a huge impact on how well the model learns.
Huge. And that leads to the whole discussion about gradient variance. Equation 10 in the paper gives a formal way to estimate this variance.
Right. And what's interesting is that while the theoretical loss function, the LE-elbow, might be the same regardless of the noise schedule, the actual estimator you use during training, that's not invariant. So the variance of the gradients you get depends a lot on the noise schedule.
Exactly. It's one of those things where the theory and practice don't always line up perfectly, which brings us to their proposed low variance noise schedules. These are all about finding that sweet spot in terms of masking.
Not too much masking, not too little.
Right, because if you mask tokens, the model learns too easily, and if you mask too many, it basically just learns the marginal distribution of each token, which isn't that useful either.
So you need to find that Goldilocks zone.
Exactly, and that's what these clipped noise schedules are all about. Instead of sampling the mask rate from the full range of 0 to 1, they restrict it to the smaller range between beta and a megabalar.
So you're basically focusing the training on a specific range of noise levels.
Precisely. And they even have this data-driven ways to learn the optimal clipping range. They basically do a grid search during training, trying different values of beta and a megadollar, and they pick the ones that minimize the variance of the ELBO estimator.
So they're adapting the noise schedule as they train.
Yeah, pretty clever. And if you look at table 2, you can see how this works in practice. They show that for different block sizes, there's this optimal distribution of mask rates that minimizes both the variance and the test perplexity.
So lower variance during training translates to better performance in the end.
That's what the data suggests, but let's get to the good stuff. How well do these BD3LMs actually perform? Tables 3 and 4 show the results on the standard language modeling benchmarks LM1B and OWT.
Right, the 1 billion word benchmark in open web text. Everyone's using these to compare their language models.
Yeah, they're the go benchmarks. And the results for BD3LMs are pretty impressive. They achieved state-of-the-art perplexity among all the discrete diffusion models.
So they're beating out all the other diffusion models.
Yeah, and not by a small margin either. On LM1B, they got up to a 13% improvement in perplexity compared to some of the previous top models like MDLM and SED.
Wow, 13%. That's a pretty big jump.
It is, and they saw similar improvements on open web text as well. So they're showing that these block diffusion models, they can really compete in terms of language modeling performance.
And remember, they can also generate arbitrarily long sequences, which other diffusion models struggle with. Table 6 shows that, right?
Yep, table 6 shows that they could generate about 10 times longer than models like SE.
10 times longer. That's pretty huge.
It is. It opens up a lot of possibilities. But of course, perplexity isn't everything. What about the quality of the generated text?
Right. Does it actually sound like human written text? Table 7 shows the results on that using generative perplexity as measured by GPT-2 large.
Yeah, so they used a pre-trained GPT-2 large model to evaluate the quality of the generated text. And again, BD3LMs did really well. They got the lowest generative perplexities compared to all the other diffusion models.
So GPT-2 large thinks the text from BD3LMs is more likely to be human written.
That's the idea. And what's even better is that they achieved this with significantly fewer function evaluations than models like SSDLM.
Which means they're more efficient during sampling too.
Exactly. And they also mentioned that qualitatively, the text just looks better, more coherent compared to some of the earlier models like MDLM.
So they're ticking all the boxes: good perplexity, long sequences, and high quality text. The ablation studies in Table 8 should give us some more insight into how those different design choices contribute to the overall performance.
Yeah, the ablation studies are always important. They help you understand what really matters. And the results here are pretty clear. The clipped noise schedules, they make a big difference.
Both in the variance and perplexity.
Exactly. And the vectorized training algorithm also gives you a nice data, around 20-25%. So those innovations really do pay off.
Okay, so we've covered a lot of ground here. To wrap things up, let's put BD3LMs in the context of the broader research landscape. Section 7 of the paper talks about this, right?
Right. So they make it clear that this work builds directly on the foundation laid by D3PMs.
Discrete denoising diffusion probabilistic models.
Yep. Some important advances. They're tackling that fixed link limitation. They're really digging into the reason likelihood gap, and they're showing that you can get significantly better perplexity with diffusion models. They're also building on work done with mask diffusion language models, MDLM, but they're going deeper into this whole issue of noise schedules and variance, which wasn't as big a focus in previous work.
Right, even though the theoretical Nielbo might make like the noise schedule doesn't matter that much, it clearly does in practice.
Exactly. And they also contrast their discrete diffusion approach with those Gaussian diffusion models like SSDLM.
Which use continuous noise instead of discrete masking.
Right. And they point out that the discrete approach has the advantage of tractable likelihood estimation.
Okay, so lots of connections to previous work. It's like they're taking the best ideas and pushing them further.
Yeah, they're really moving the field forward.
So for our listeners who've been following along, what are the key takeaways about block diffusion language models?
I think the big takeaway is that BD3LMs represent a real breakthrough. They're combining the best of autoregressive models and diffusion models. They're addressing key limitations that are held back diffusion models like fixed length generation and inefficient inference.
And they're doing it by being really smart about how they handle the noise during training.
Right. That whole focus on variance reduction as clipped noise schedules, that's a big part of their success. And the results speak for themselves. state-of-the-art performance on the benchmarks, the ability to generate long, high-quality text, and the potential for even faster inference with KV caching.
This has been a fascinating deep dive. It's amazing to see how quickly this field is advancing.
It really is. Who knows what they'll come up with next?
Before we go, let's leave our listeners with a thought to ponder. Imagine what we can do with these BD3LMs. We can generate long, coherent text, potentially even faster than with AR models. Think about the possibilities.
Yeah, think about content creation, chatbots that are actually engaging, maybe even scientific applications. The paper even mentions using diffusion models for things like biological sequence modeling.
It's mind-blowing. So we encourage you to check out the paper, explore this area further. Who knows, maybe you'll be the one to come up with the next big breakthrough. Thanks for joining us on the deep dive.